Okay, this is lesson 3.3b. Let's remember from last session, because you might not have caught this. So when transforming data to a power model, when I say power model, we're talking about you take either x or y, you square it, you cube it, you square root it, you cube root it. Those are power models, putting something to the second or third power or second or third root. I guess you could go higher than that, but we typically don't. So that would be a power model. So if you took the log of both sides, both x and y, then it should produce a linear pattern. That's one way of knowing that it's a power model. Sometimes it's just obvious because the dimensions of one is one-dimensional and maybe the dimension of y is three-dimensional. So power model makes more sense. But sometimes it's really hard to figure out if a power model makes sense or not. So you could just take the log of both sides. Is the data linear? You could just go with that. Actually, you just go with log of both sides or use the power model at that point. So what if x and y have a relationship that can be described by an exponential model? So exponential model is when we have x in the exponent. So classic kind of like a times b to the x power there. So when x is in the exponent, like our money grows exponentially. We studied that in Algebra 2, that kind of stuff. So if it's exponential, then a scatter plot of the log of y against just regular old x, not the log of x, should produce a roughly linear association. So now we have a way to see if it's exponential or not. And so you can use logarithms to prove why that's the case. But let's just look at a few examples here. So Gordon Moore founded Intel, in that the number of transistors in an integrated chip circuit would double every 18 months. This is called Moore's Law. It helps us, advance computing. So here are the data on the number of transistors. And so the data is, here's a picture of it off to the right there. And you can see this does look like at some point here, it starts becoming exponential growth here. It's doubling every 18 months, evidently. So here's the scatter plot from 1971 to 2016. And we use years since 1970 for the x-axis there. And so it does seem to look like an exponential model there, but let's see what happens here. So if we take the log, or it doesn't really matter if you do log or natural log of the y variable here, but this would be the test to see if it's exponential. If you take the log or the natural log of the y variable, plot that against the regular old x variable here, is that data somewhat linear here? And I think it is. And so this seems to be an exponential model here. It's a very linear pattern, so exponential model seems reasonable here. So here's some computer output from the regression. Be sure to define any variables again. So we did the natural log of y, but the x variable was just years since 1970. So if you write the equation there, it's going to be the natural log, the predicted number of transistors of the natural log. Wait, how do we say that? Natural log of the predicted number of transistors. I think that's how you would say that. But you can't forget that ln in the equation again, because we did that before we took the regression. And the x variable is just plain old years since 1970. Of course, our constant there is 7.22. That's our y-intercept. And the number below that is always the slope in Minitab. So that's 0.3542. Use your models to predict. So 2020, so years since 1970, so you have to subtract there to get 1970, would be 2020 minus 1970. So we're plugging in an x value of 50 there, because it was years since 1970. So if you plug in 50, you get this. And now at this point, you have a choice. So some folks, when they get to the second line there, okay, so they get to the line there where it says natural log. I like to write it like this, natural log of transistors, I'm just going to use X there, the predicted transistors, equals 24.9372. So you have a choice. You could use actual math to solve this. So if you do that, you have to understand that the base there is e. So if you convert this to exponential form, it'd be e to the 24.9372 equals the x variable there. And then you just type that into your calculator at that point and solve it that way. The other way is get your calculator out and use the solve command. So menu 3.1 is solve. Type in natural log of, you can just type it, of x equals 24.9372, comma x. It should solve that equation for x, and you get the it's 6.76 times e to the 10th power there. So that's where that number comes from. I think we would probably accept it in scientific notation or in the actual number there. I would think we might accept both. So this would be times 10 to the, I think it was 10th power, if I remember right from the calculator. So either answer. This model predicts an Intel chip made in 2020 will have about 68 billion transistors. So the number of transistors, the unit there is transistors. That is something we like to see. We like to see units on the answer here. So I'm not too worried if it's scientific notation or the other number, but the units we want to see. Suppose a scatter plot shows a curved relationships between the variables x and y. So let's see. So if we see the first one here is just braking distance versus tread depth. They're talking about correlated to the amount of tread on the tires that are left. So researchers collect data on braking distance along with the tread depth. And here's the linear regression. So you can see this seems to be some kind of curved pattern here, non-linear pattern. So definitely not, we're not going to stick with, when you see the residual plot here, this is just braking distance versus tread depth, just x and y there, or y and x, I should say. It's always y versus x here. So braking distance is y, tread depth is x, and that doesn't seem to be a good model there because the residual plot has a curve pattern. So if we try just taking the log of both sides, so log of the y value there, braking distance, and the natural log of the tread depth as well, we can see that this doesn't have a curved pattern to it. It's somewhat scattered. So this seems to be good, which means it's a power model, is because a linear fit is a good idea here. If we just take the natural log of the y value there, braking distance, then our residual plot has a curve pattern, which shows that this is not an exponential model here, because again, if you just take the log of y, it should give a linear, if it's exponential, it should give a linear pattern. And here the residual plot says this is not linear, so this is not exponential in nature. And again, the reasoning is, you look at the residual plot for taking the log of both sides, it's got to be a power model there. Produce the most randomly scattered residual plot with no leftover curve pattern. It's the most appropriate model. So we would just stick with that model at that point. So if you use that model, here's the output, natural log of the y value, braking distance, always y versus x, natural log of tread depth, and so there's the values there. So if you just write your equation in context, it's the natural log of the predicted braking distance equals 2.9. We get that from next to the constant there, that's the y-intercept, and then minus the slope there is 0.2690, always underneath the y-intercept, times the natural log of tread depth. So don't forget, we took the natural log of both sides here, so we've got to use that. In this case, again, we get to this step where it's natural log of braking distance equals 2.608. You have a choice. You could, use math to solve that. So you could say natural log of x, or whatever variable you want to use there, equals 2.608, just to remember, 2.608. So that's really base e, so this would be e to the 2.608 equals x. So you could just type that in your calculator at that point and get the answer of 13.57, or you could have used the solve command again and solved that way. I don't care which way you do it. That's a good step to show to get to this point, and then just show your answer at that point if you want, if you used your calculator. So that would not be a problem. And then, of course, you want to talk about that in context. So the answer was 13.57. Oh, sorry. So use the model to find this. So it's 13.57 car lengths as the unit for that particular answer. Okay, part B, use the model chosen in part A to calculate and interpret the residual for the trial when the tread depth was 3/32 of an inch and the stopping distance was 13.6. So we took the natural log of both of them. In this case, we plugged in, so the residual. So, okay, so here we're finding the residual. Okay, the residual is the actual minus the predicted, right? So the actual is 13.6, that was given to us in the problem. The predicted braking distance was 13.57. So the actual minus predicted would be 13.6 minus the one we just found. So in part B, we're using our answer from part A to get 0.03 car lengths. That's a positive number. That means our prediction was lower than the actual car length. Okay, so when the tread depth was 3/32 an inch, the car traveled 0.03 car lengths further than the distance predicted by the model using, again, the natural log of both the x and y there. Okay, let's try one, and let's try this in the calculator. So this is, I guess, where it gets a little tougher. The fact that this book does a very good job of getting you ready for the AP, only has one question on the homework or a couple where you have to actually do it yourself. And the calculator tells you that most of the time, if this is a question on the AP, they're going to give you whether you're doing the natural log or not or something. But we might have to do this in our calculator, so I'm going to show you how to do that. Okay. So the first thing I want you to do is go to Listen Spreadsheet page, and I called one position or posit, and then one click for the y values. I'll put in that data into my calculator. So go ahead and do that. And let's just go look at the scatter plot here. So if we look at the scatter plot, we choose position for our explanatory and click for our y. Ooh, so this is definitely curved. It does, if I had to guess, it does look kind of exponential, just looking at it, but I don't know. So if you go back to the previous page, control left arrow is go back. I'm going to take the log of both sides. So I'm just going to take the log of both sides. So natural log ln of posit is the name of my x-axis. Oh, so here I need to just call it ln posit with no parentheses there. That's the name of it, so I know what I'm clicking. If you click the equal sign in the formula bar, now I use ln parentheses posit, because that will actually take the log of that side. If you'd rather just click the button down here, there is a natural log button if you have good eyes. It's above e to the x. So you control e to the x and then type posit. If you'd rather not type posit, you could click the variable key and choose posit from that. And press enter, and it should populate. The only thing weird is it gives you the exact answers because this is a CAS calculator, but it doesn't really bother us because we're going to graph that anyway. But you could put a decimal point in the problem if you wanted to get decimal answers there. Now we're going to take a natural log, so I'm just putting ln in front of click. So ln click is going to be the name of it, but in the formula I'm actually going to type in ln parentheses click because I want that to calculate all the different values there. Okay, so now we're going to graph that guy. So hit the home key, go to data statistics, and we're going to go ln of posit versus ln of click. Whew. So it is still curved, which means this is exponential. My guess there, I guess, was right. I didn't know, I was just guessing. So now, because we know it's exponential, we should take the log of the y variable, but keep x just regular. Okay, so let's try that. So hit the home key. X is just regular posit right there. But we want y to be the natural log of click. Ah, finally, it looks somewhat linear. We can do a linear regression here. So let's go to menu, analyze. I think it's under regression, a plus bx. Yeah, it's not bad, 0.99 for correlation. I like that a lot. You would then take that equation right there and the y varies being predicted, and we're going to talk about that in context. So the predicted number of clicks equals 3.37 minus 0.329 times the position. Okay, so the formula there, your answer would be, so this is actually, I thought this was interesting to read the answers here. But part C, that would be the equation, which was natural log, the natural log of the predicted y variable, which is click-through rate, equals 3.37 minus 0.32 times the position of the website. Okay, so I thought it was interesting to answer choice B here. Is it exponential? Because the relationship of natural log, right, and position is roughly linear, and click-through rate seems to follow an exponential model. A power model would not be appropriate because the relationship between the natural log and the natural click-through is clearly curved. So they're saying the same things, but I just wanted to, hopefully by the end of this lesson, that's kind of caught on. So now you understand, you take the log of both sides with the power model if it's linear. Take the log of y, it is exponential in nature. So that's how you tell the difference between the two. So that's why we spent 2 days on the lesson, because I think that's a nuance that when you first learn about transforming data, you don't always pick up. But then when you do a little bit more of it, maybe it makes more sense. Okay, that's the lesson for today.